Alright, so who we are. I'm Mike Kershaw, also known as Dragorn. I did Kismet and Kisbee, and I've been working with Mike on Project Dice Show and some random other hardware and software stuff.
I'm Michael Ossman. I'm the founder of Grey Scott Gadgets, and you might know me from projects like Ubertooth or HackRF. We're here to talk about these various hardware projects that we're involved with and to hopefully encourage some of you to get into hardware. Full disclosure, we really have no idea what we're doing. This is all new to us. About 4 years ago, neither of us knew any of this stuff. We had no experience in hardware. We were just software guys. And we're going to try out repositioning Dragorn's mic here. Want to do a test?
Test.
That's much better, as long as we can avoid the feedback. Hopefully some of you will get the impression from this talk that maybe getting into hardware, if you're a software person, might not be such a scary thing.
Alright, so why do we want to sniff stuff anyhow? So wireless protocols are always fun. You can see what's going on in the air around you. Are some devices considered protected only because no one's ever tried? For a long time, Bluetooth was considered unsniffable. It's not. BTLE, Bluetooth 4 stuff, is very sniffable, very easily, and the encryption on it is crap. So people consider it secure, but it absolutely isn't. If you're doing site security, can someone be running a weird radio dumping data out of your site? You know, if they're running Wi-Fi on 900 megahertz, you're never going to see it with a normal radio. Maybe you're just curious. That's a good enough reason. Maybe you need to look at either something very old with a crappy, weird old radio, or something very new that nothing else talks to yet. Maybe it's just pure spite. Some vendor went, no one can ever interfere with this device. It's some weird encoding, whatever. We don't need to encrypt it. Well, you do, because you can. So you might need to make your own hardware, because some protocols are really easy to sniff. Wi-Fi, for example, any commercial card you get, monitor mode, you're done. Some are really hard to sniff, like Bluetooth. You can't do it with a commodity Bluetooth client device. Some would be easy to sniff, for example, Zigbee, except no one makes affordable Zigbee sniffers. Some are easy to sniff, but are really expensive. So you can go buy a gig E-tap or a USB 3 tap. They'll be, $2,000 to $10,000. And custom protocols, there isn't going to be commercial hardware to do it already anyhow. So fortunately, we really live in the golden age of hardware hacking. It is incredibly cheap to make a PCB. If you wonder if you should solder a bunch of wires together or make a PCB, just make a PCB. If you're doing anything that involves high-frequency radio, you're going to be making a PCB. You really can't get around that. You can do a 4-layer board for complex RF with solder paste stencils for probably $50, probably even less. The tools to build the stuff are also really cheap. So when in doubt, just make a circuit board. You can get free software to do it, 100% cost-free and, GPL-free. Surface mount components are often a lot cheaper now than through-hole components for the same functionality. And anytime you're going to need to make, 2 or 10 or 30 of these things, make a circuit board. Future you will be very happy that you did when you don't have to debug 30 wires cross-patched all over the place and you can't figure out what you did.
So we have this little checklist of various considerations that we think are valuable to make when leaping into one of these projects. And the first thing that we always consider is there an existing integrated circuit? Is there a chip that does most of what I need to do? So can you get an existing IC to sniff Zigbee? Well, sure. There are lots of existing chips that can sniff Zigbee. So if you want to make a Zigbee sniffer, and there is no Zigbee sniffer around that does what you want it to do, well, just look through the different chips that are available and say, hey, this one I should be able to use to do what I want to do, and build a board around that. That's always going to be the easiest, most cost-effective solution to sniff one protocol. If you have one particular target device or one particular target technology, if you can find an integrated circuit that does what you need for that one technology, that's going to be the easiest path to take. Now, some protocols don't have an integrated circuit available that could actually be used to just sniff them. Bluetooth, for example. Sure, there are a lot of Bluetooth chips out there, but none of them have the capability to passively monitor other Bluetooth connections. So for one of the projects I'll talk about later, the Ubertooth project, I had to just take a completely different approach instead of just using an off-the-shelf chip. But for some of our projects, like the Zigbee sniffer we're going to talk about, we were able to find an integrated circuit to help us out. And the protocols that don't have commodity ICs available, when you're trying to sniff one of those, you're going to need something more general purpose. You might be able to do what you want using a software-defined radio approach, or you might be able to do what you want using kind of a logic analysis approach. You might need an FPGA or something more complicated, but it's going to end up costing more and being more complicated and requiring more power and so forth than a fully integrated solution would. Software-defined radio, SDR, is the general purpose approach where you can digitize any radio signal and analyze it in software. Software-defined radio turns hardware problems into software problems. And if you're a software person and you're just kind of dabbling in hardware, then that's kind of that might sound like a really attractive approach, because you can have minimal hardware or kind of universal hardware and then do all the hard stuff in software. But there are some advantages and disadvantages. Software-defined radio is very similar to software-based audio solutions, right? Except instead of having a sound card with a microphone and a speaker, you replace that microphone and speaker with antennas. It's basically the same kind of thing, except it operates about 1,000 times faster because radio waves are much higher frequencies, much higher bandwidth than audio waves. But SDR is great because it lets you deal with arbitrary radio signals. It doesn't matter what the radio signal is, as long as it's band limited, it isn't wider than the amount of bandwidth that your SDR receiver supports, then you can receive and demodulate and decode that target radio wave. It also lets you do a lot of projects without actually having to do any hardware, if you can just find somebody else's SDR receiver that you can build off of. But it has some drawbacks too. It's going to be more expensive than the special purpose solution. Maybe not more expensive to develop, but more expensive to deploy. So sure, you make a solution where you can sniff one thing, that's great. But then 100 other people say that they want to replicate what you did. And if you can say, well, buy this $1,000 SDR platform and that will let you do what I did, you're not going to get very many takers. But if you say, here's a platform for $100 that lets you do what I did, then you're going to get a lot more people replicating your work and actually able to take advantage of it and use it in day-to-day places and build upon it. SDR has that disadvantage of cost and power supply, where you're not going to make the smallest, most cost-effective, most power efficient solution using the SDR approach. Logic analysis is just monitoring the signal voltage levels on different wires. So if you're doing wired communication monitoring, you can often use a logic analyzer or the logic analysis approach, which is just looking for transitions to see whether these wires are having a high voltage or a low voltage and logging that over time. And we kind of think of this as being vaguely equivalent to the SDR solution. SDR is used for monitoring wireless communications, radio communications, and logic analysis is used for monitoring all sorts of different wired communication protocols. And you can get some off-the-shelf tools for logic analysis, just like you can get some off-the-shelf tools for SDR. And depending on what you need, that might be sufficient. You also might need to, in some cases, kind of roll your own logic analysis solution. And this becomes, this is generally a very easy approach to take for lower speed communication systems, but a harder approach to take with higher speed communication systems.
All right, so the next thing you have to consider if you're going to go ahead and build your own hardware is how technical is your audience? If your audience is really technical, you can make your hardware a little more fidgety, maybe it needs some more advanced knowledge to use. So, if you're releasing it for for hackers or for technicians in your department or something, then maybe telling them they have to solder some stuff together or that they have to compile their own firmware and whatnot isn't such a problem. But if you want to be able to mass distribute it to people, or if you have like cable technicians or something like that that go out into the field that don't have these skills, you need to worry about making it more polished. Having it in a case is even a big deal sometimes for people. They don't want to compile their own firmware. They want it to come pre-flashed. They want it to come pre-assembled. But don't sacrifice capability for simplicity if you can avoid it. So if you might make users' lives a little bit more difficult, but if you document it well, it's worth having the extra features available to them than cutting it out because you assume no one will be able to handle it.
Are you going to make more than one of these things? That's a really important question to keep in mind when you start a new project. Because if you're making just one, then the cost of the individual parts you choose really doesn't matter that much, right? If you're going to spend more on a soldering iron than you are on the actual components of your project. If your tools cost more than the actual parts you're using to build something, then the cost of the parts is kind of lost. And so it doesn't matter if the integrated circuit you want for your project costs $5 versus $10. If you're just making one of them, it really doesn't matter. You should use whichever one is better, more available for your solution. But if you're going to make more, if you think that a dozen of your friends are going to want to do what you're doing, then you have to start considering the more factors, especially cost and volume discounts. Most components have a volume discount available if you buy more than one. Some components have a volume discount available to you if you buy more than hundreds. And it really varies from part to part. It also varies on what your supply chain is. But let's assume that you're just buying stuff from online distributors that anyone can order from. You're going to find some variation. Now, personally, it took me a long time to get to the point where I kind of learned to just always sort by price at 1,000 or 10,000 quantity. It sounds silly. Like, I've never made, I now have a business where I make and sell hardware for people, and even so, it's very rare that I order anything in like 10,000 at a time. Usually I get maybe 1,000 Ubertooth Ones manufactured at a time, for example. I'm not ordering stuff in tens of thousands, but when I sort by price on an electronics distributor, component distributor's website, I just always sort by 10,000 now, even if it's just a one-off project. And I might go back on what I said earlier, that if you think you have a one-off project and you don't care about the cost, you might be wrong. Down the road, you may say, hey, this project worked pretty well. I think I might want to make more of them. Or I released the source code for my project and somebody else wants to make more of them. And as soon as that happens, you will be glad that from the get-go you selected a component that cost half as much as this other part at high quantity. And the relative price that you get on a component at 10,000 quantity of component A might be half the price of component B at 10,000 quantity. But it might be the other way around at one quantity. It might be that component B looked like it was less expensive, but it really isn't once you get to the point where your project gets adapted to something new and you're suddenly making a whole bunch of them.
All right, so then you also have to determine how much bandwidth do you need to communicate whatever you're doing. So interfacing to computers is easy. USB 2 is great. USB 2 is cheap. USB 3 is fast for almost any definition of I need a fast communications protocol. libUSB lets you interface on multiple platforms. There's quirks, but you don't have to write a kernel driver to make a custom USB device now. Just do libUSB, a couple calls from user space. The Android USB API is almost the same as libUSB. You can consider weird things like PCI Express if you really, really think you need it, but you're into scary territory, and you probably don't, and certainly not for a first project. For mobile devices, it's a whole different story. Apple makes iOS basically impossible to talk to, unless you talk about a jailbroken phone, and that's a whole other level of user support issues that aren't worth really considering. On Android, you've got Bluetooth or you've got USB. You can do serial over Bluetooth. It's really low bandwidth, but it's cheap as hell. You can get Bluetooth modules for $6. It works great, and every Android phone really supports Bluetooth. You can do USB host, kind of. Manufacturers always manage to screw it up. There's only about 5 phones that I can recommend that really work reliably. The only high bandwidth option you have is USB. Sometimes you can hack around it. So here's another reason to make your own circuit board. I could have soldered together a whole bunch of wires and a battery and a USB hub to try to make Motorola phones work, or I could spend $1.20 on a circuit board. So there's a hack to make Motorola phones do USB host correctly. With iPhone, Apple doesn't like other kids play with their toys. There's a serial interface in the old 30-pin connector. It requires licensing and special chips to talk to it. Lightning requires licensing and special chips to talk to it. Bluetooth, you'd think, oh great, they work with Bluetooth, not with serial port protocol, requires a special thing with licensing to talk to it. You could root it, but how do you support people telling people they have to go jailbreak their iPhone before they can use your product? It pretty much, it eliminates iPhone unless you have enough money to license stuff from Apple. And then finally, how do you integrate with existing tools? There's a ton of tools out there. It is worth your time to integrate with them. There's Wireshark, there's Kismet, there's Zigbee and Lorcon, there's GNU Radio. They will do most of your work for you if you can get your data into them. So Wireshark is designed to read from network interfaces. It'll do it great. If you can get your packets to look like they're coming from a network interface, you're already done. If you want to add additional protocol dissectors for whatever your thing is, so USB dissectors, Wireshark dissects USB just great now. Nothing to do with networking, but it's a great platform for doing it. You can make a fake network device with TUNTAP. You can make a PCAP file, and you load it into Wireshark. I'm currently working with Mike Ryan on extending Wireshark to be pluggable for things that aren't network interfaces, so you'll be able to just pick a USB device and have it capture directly from that with whatever libUSB protocol you specify. We're giving a talk on that at SharkFest in June, so hopefully it should be done by then. So with Kismet, the current stable code was strongly designed for 802.11. I'm working on a new version called Phi Neutral that will treat everything as sort of some sort of device, and it might be 802.11, it might be Zigbee, it might be Bluetooth or whatever. So it'll be a unified UI and a unified log, and plugins will get all the benefits automatically. So I was significantly inspired to do this by Ubertooth, where Mike started working on the plugin to support that and had to duplicate all the GPS and tracking code and whatnot, and that's just silly. So if you do anything that you think could plug into Kismet, it gets you free GPS logging, gets you free signal logging, it gets you XML logging, PCAP, live export to Wireshark, and basic UI support with very minimal code. I think the Ubertooth plugin for the Phi Neutral code is 300 or 400 lines on top of the Ubertooth code base. As long as you can get something that looks like a packet and has something that looks like a MAC address, you can tie it into Kismet now if you use the Git code. So here's a quick example of the early version of the UI where there's Wi-Fi and scanning mode Bluetooth in the same UI listing. There's also GNU Radio. It's designed for waveforms, not packets, but it's basically how you get raw data to look like packets later. So you can define input and output blocks for chained operations. So if you're making something that looks like an SDR, you just write a new capture block that imports that data. GNU Radio doesn't really care what provides the data. So there's already the USRP, there's the RTL SDR, there's HackRF that Mike's working on. Osmo SDR is a great example to start from, where they already support HackRF and RTL and FunCube, I believe. So if you're actually going to go through and do this, you want to check out the pre-made tools, you want to think about what processor and firmware options you have, and you want to start looking at how you're going to design the board with CAD. If all you have to do is talk to a chip or a module as a one-off, and you're not really looking to build a whole platform from scratch, you've got the Bus Pirate, which is 20 or 30 bucks. It can talk almost all the inter-chip communication protocols in serial, plugs in over USB. Great little tool. Arduino can talk to a ton of devices, LCDs, flash chips and whatnot. There's libraries for all of that. The GoodFET also does a ton of chip communications. It's a great opportunity to learn to solder because Travis will not ship you an assembled one.
Although you can buy a pre-assembled one from Adafruit now.
That's cheating.
That is cheating.
Unfortunately, a lot of the high-speed stuff in RF is going to be surface mount only, so you're going to have to build your own board. You won't be able to just buy a radio chip for Zigbee and slap it in a dip socket or fly wire it into an Arduino. You're going to have to build some sort of board underneath it. Some of them require very expensive custom programmers. Sometimes you can hack around a very expensive programmer. The programmer for the Atmel Raven is about $400, or as Mike discovered, it's about 5 cents in wire. Basically, this just pulls out the pins for the old style programmer that they didn't bother putting through.
It's 5 cents in wire, but more than 5 cents in effort. It's kind of a tricky soldering job. One way or another, your hardware platform is going to have some kind of a processor on it, probably some kind of CPU. For software-defined radio approach, if you're building your own SDR type of platform, you're going to need something that has a lot of throughput, something that can move bits around at a pretty high rate. Usually, like at least an order of magnitude higher rate than you would need if you're doing a handling packetized data. When you're dealing with raw radio waveforms, you need an order of magnitude more speed than you do when you're dealing with packetized data. Take a look at all of the options that are available to you, and especially the support and tool chains. Like there are plenty of CPUs that have free compilers. You can find support for a number of different CPU architectures in GCC, for example, or SDCC, the small device C compiler. But there are some microcontrollers out there that might look like an attractive option until you find that there isn't a good, well-supported, already free-to-use compiler out there for you. Take a look at what the tools that are available to you, and also take a look at what is built into the chip itself. Microcontroller. A microcontroller is just a CPU with a bunch of extra add-ons on chip that's generally small and low power, and it's like a whole computer in one tiny little package. And what we call peripherals are actually on-chip features that are in addition to the CPU core itself. So it's kind of like having your whole PC shrunk down onto a chip, but a really old PC. And the peripherals are things like the cards that were in that PC, for example, also shrunk down onto the same chip. So you might have a peripheral like an ADC, an analog to digital converter, that can be very, very handy for these kinds of things. Almost every microcontroller has GPIO capability, just general purpose I/O, and all that means is that it's able to just set one of its pins to a high voltage or set it to a low voltage as an output, or read an incoming high voltage or low voltage as an input. And it's just a binary in and out that can be applied to a whole bunch of different pins on the microcontroller. A UART is a very common peripheral, and it's just a serial port. So just like the old serial ports you might recall if you ever used a modem and connected it to a PC, that serial connector is a type of UART, which in that case is using RS-232 signaling, which is kind of crazy high and low voltage levels. It actually swings like way below 0 voltage. But these days, it's much more common, especially if you're dealing with embedded electronics and just talking to your microcontroller itself. Your microcontroller isn't going to implement RS-232 voltage levels, but it is going to implement the UART part of that, which is serial communications at just logic level voltages like 0 to 3 volts or something like that. And so if you want to get RS-232 in and out of microcontroller, you typically have to have a voltage translation IC in between the RS-232 interface and the UART on the microcontroller. But most of the time we just skip that step these days, and we just do what's called TTL level UART, which is just logic levels in and out of the thing. SPI or SPI and I2C or I2C, those are inter-chip communication protocols, which will become handy anytime you have multiple parts on a board that need to talk to each other. They're also handy for getting off-board communication sometimes, like the Bus Pirate and the GoodFet that he was mentioning earlier, or if you have an Arduino that you want to talk to. Those like short off-board communications can be implemented with these pretty simple serial communications protocols like SPI and I2C. in general, that's going to become very handy. A lot of the projects that we work on have things like a microcontroller and a transceiver of some kind. Like it might be a wireless transceiver, or it might be a wired transceiver. But whatever it is, it probably talks to the microcontroller over SPI or something like that. And so we end up using SPI a lot, and I2Z maybe not quite as much. So you're going to need firmware or some kind of software for whatever kind of device you pick. In most cases, we have a microcontroller, and we write firmware for it in C. If you're a software person, you probably know C, or at least some C-like language. And so it's fairly accessible to get into programming for microcontrollers because it's just C. And as long as you have a compiler for the target CPU you're interested in, it's really no problem to just write some C code and compile it and blow it onto the microcontroller and try it out. FPGAs are a little more complicated, field programmable gate arrays, and you have to write code for them in a hardware description language like Verilog or VHDL. These are a little bit of a leap, a stretch, if you're familiar with, if you're more of a software person and you know things like C and Python. Getting into hardware description languages is a little bit of a leap, but it's not that crazy. There are plenty of resources around online that can help you learn that stuff. Most of the time, though, for most of these projects, we're avoiding FPGAs. We're avoiding that extra complexity and extra cost and extra power consumption. The only times we use FPGAs is when we absolutely have to, like when we really need super high-speed stuff. We'll talk about one project later on where we really are using an FPGA. Beware of license issues on sample code for whatever kind of CPU you choose. This is a big, big deal. Also beware of the tool chains and whether or not they're free to use, whether or not they're open source. If you are trying to make something that is open source, this is a really big concern for you. If you're just making something for yourself or for internal use at your company, whatever. But we are open source developers, and we originally did a lot of open source software, and now we're doing a lot of open source hardware. And I'm sure many of you are active in the open source community. And if that's a concern for you, then you have to be very careful. There is tons of sample code out there for that, like an ARM microcontroller. Somebody releases an ARM microcontroller, and the manufacturer releases all this sample code and stuff that will compile out of the box on a proprietary compiler. And so you have to go through the effort of like porting that sample code to run to be compiled with GCC. Okay, that's step one. But then step two is, oh crap, this sample code has a license at the top that isn't really a license. It just says all rights reserved. And if it doesn't have an actual open source license, you can't really build open source software out of it and just put your own license on it. You have to rewrite all that stuff from scratch. And we have done that on more than one occasion. Just like completely from scratch, written all the hardware support libraries for the peripherals on a microcontroller, for example. If you can find a part that already has open source libraries, then you're a big step ahead in developing an open source project. And you might want to keep that in mind right early on when you're actually selecting a part for the project.
All right, so once you have the data, you have to send it to the PC. So you need to make sure your comms have enough bandwidth. USB 2 is 480 megabit. Sounds like a lot. Disappears fast depending what you're doing. If you're using radio frequency stuff, make sure that you're not overlapping what you're talking at the same frequency as what you're listening. So if you're doing Bluetooth, you might have a bad time listening to anything else on 2.4. You can do it. I do it with Zigbee. It works pretty well, but be careful. And if you're trying to listen to something that's a lot quieter than, say, Zigbee, you're going to have a hard time with your own signal stomping on top of it. USB 2 is pretty cheap and easy to do now. USB 1 is dead cheap and easy to do. USB 3 is much, much more complex, but we'll cover more of that later. So on the host side code, it's what's going to talk to your firmware. So you need to get the data from the device somehow. If you're doing libUSB handles raw interfaces. It's great. You can just, get a bulk read 512 bytes at a go as fast as you can, saturate USB 2, it's fine. Otherwise, if your chip talks USB serial, it's pretty handy. Most platforms support it. You don't need a lot of other code. It works with standard serial stuff like Pi serial. It's a good way to go. If you can get away with it. Bandwidth is an issue. I've never tried to saturate USB 2 with serial. I don't think it would work very well because of the framing. If you somehow have Ethernet output on your device, for example, if you're going really high-end, like the USRP2 uses gigabit Ethernet for its communications, you can just capture with TCP dump or libpcap or whatever if you wanted. So how do you actually start making these things? It's only 4 steps. It must be simple, right? You make the schematic, it's easy, and then you make some drawings and route the PCB, and then plot the CAD files and email it to someone, and you get a circuit board back, and it all works. It's great. Simple. So for the schematic, I just like this one. So the schematic is it's basically like the old electronics magazines, logical drawings. So some CAD tools have a really strong distinction. So you make your schematic, and that's one thing, and then you assign parts to everything in your schematic, and then you make your PCB, and that's a completely different operation. So KiCad works that way, and some of the commercial CAD software works that way. Other tools like Eagle treat them as much more unified whole, where your processor drawing in the schematic is directly linked to that processor type. So you can't go, here's the chip in the Arduino, and then I'm going to make it surface mount this time and dip the other time with all the through-hole pins. In Eagle, you can't do that. In KiCad, you could. So in the schematic, the parts are organized for layout and logical representation. It's the description, not the blueprint. So your pins might go like 1, 3, 9, just because they're all the same type of pin, and it wants it to make it easier for you. Compared to the PCB, the routed PCB, which will be basically the drawing that is printed onto the copper to make the circuit board. You've got dozens of choices for this. Mike and I both use KiCad. It's GPL, it's 100% free, and there's no license encumbrances, which is a big deal because for some software like the free version of Eagle, you can't sell a PCB you generated with the free version. I don't know that anyone's been gone after by them, but I'm also not sure exactly where they draw the line about selling. Can you sell it as a hobby level and not commercial level? We'd just rather use something that's completely free. Eagle, the free version, is also limited in how physically large a board you can make, and you can't make it more than 2 layers. You can still do a lot with that. There's nothing wrong with Eagle. A lot of people like it. Pick whichever. If you have a company's budget behind you, go get OrCAD or Altium or something. What are they, like 15 grand per seat?
I have no idea how much they cost.
They're a lot of money. So KiCad is it's pretty nice. It's capable of doing pretty complex boards. Open source is good because you can modify it if you want, if you really want to get into whatever their drawing code is like. I don't. It's also an open source UI, and I think everyone kind of knows what I mean by that. It's a little quirky, and sometimes upgrades between versions of KiCad don't go all that well. Tutorials are getting a lot better now. For a long time, there were no tutorials for KiCad. They're a lot better now. They're on YouTube. I have links at the end to some of them. Learn the keyboard shortcuts. It's very badly documented that everything has a keyboard shortcut, and it's basically unusable if you don't know that they're there. The predefined library of parts is growing. It's pretty easy to make your own. Key for us is you can do arbitrary sizes and arbitrary number of layers. The output files are all text, so it's source code management friendly, and you can script making complex parts if you want with just bash and echo. Unfortunately, for high complexity boards, KiCad really sucks. It won't help you do things like matching trace length if that matters for what you're doing. Commercial software would. I really kind of call what KiCad does if you get complex enough to be write only, because if you go try to move something, it's just going to puree your board and you're going to be sad. And sometimes it does really, really weird things. You can kind of see there that that's a little bit of this existing circuit board, and all the rest of the screen is one pad. It decided it needed to zoom it by 4,000%. I don't know why.
So there are a whole bunch of different types of electronic components that you can use and place on your board. And the 2 main types are through-hole components or PTH components and SMT components, surface mount technology. In general, people who are new to electronics are usually kind of more afraid of surface mount parts, and they want to start with through-hole components. But that's not necessarily the best way to go for a new project. It really isn't that hard to work with surface mount technology in most cases, and I would encourage you to head in that direction if that seems like an appropriate direction for your project. Sometimes you can pick. Sometimes you have the ability to do a project with through-hole parts, and sometimes you can't. Oftentimes, the limiting factor is going to be, well, there's a transceiver circuit. There's this integrated circuit that I can buy that is the one part on the market that actually does this one incredibly important thing for my project, and it happens to be a surface mount part. Well, if that's the case, just go with all surface mount for your project. You won't regret it. 0603 components are very, very common. We use them in a lot of our projects. They look really small. And what the numbering system means is that this component is 0.06 inches by 0.03 inches. That's what 0603 means. So when you see a component listed as size 0603, that's how big it is. And it looks worse than it is. They're really not that hard to work with. You have some fine tip tweezers, and you can move these around pretty easily. 0201s are they are as bad as they look. They really, you want to avoid these if you possibly can for things that you're assembling by hand. And even if you're if you're paying for somebody to do automated assembly for you, even they might have problems with them, and you need to check with them before you use components this small, because they may have equipment that doesn't do 0201s or it doesn't do it very well. In between, there's a very common size. I don't know if we have a slide for it. We don't have a slide for 0402s. 0402s are in between the 0603 size and the 0201 size. And 0402s are the smallest components that we routinely use. They're a little bit tricky to handle by hand, but they're not unreasonable. You just have to order a lot of extra parts, because you'll be moving around with tweezers and then you accidentally just put a tiny bit too much pressure in the tweezers and ping, you just lost a part. That happens all the time. Fortunately, they cost like 1/10 cent each, and it doesn't matter.
One important thing I forgot to put in the slides was that metric and imperial measurement. So 0402 metric is 0201 imperial.
Right.
So if you're ordering parts and don't look carefully, Mauser is a big offender on this one. DigiKey, not so much. Mauser likes to add metric measurements in there, and because they all are in the same pattern, you might end up with a pile of quarter the size of a grain of rice, and you go, well,
right.
That's garbage.
Yeah, and most of the industry uses these English or imperial units for most of their package size measurements. When you see things like 0201, 0603, most of the time those are related to inches and not to a metric. It gets a little confusing though when you look at the actual documentation for the part. Like, you download the data sheet for this QFP package and you look at its size and like the spacing between the pins and everything. You look at its diagram, mechanical diagram, and it'll all be in units of millimeters usually. So they're just kind of different conventions for different aspects of the industry, unfortunately. I think the lesson here is always specify your units. No matter what you're doing, just look and make sure somebody else has specified their units and you are specifying your units. QFPs are very common. It's just a surface mount solderable package that has pins that come out, kind of gull wing shaped pins that come out. They're pretty easy to solder. QFNs have no leads, and these are a little harder to solder. And one of the hardest things about them is that they often have a pad, big square pad in the middle that needs to be connected to ground. Some QFNs you can get away with not connecting that, but many, especially RF chips, you must connect that pin to ground. And especially if your chip is one that happens to generate a lot of heat, that's usually where the heat goes, through that pad. So if you don't connect it, you can run into problems. And we use these all the time, however. They're really not that hard if you use hot air for example. BGAs, I would recommend you avoid unless you absolutely need them. It's a grid of little solder balls. But you can actually use these in your home project and assemble boards maybe on a hot plate or with hot air using BGA.
All right, so some quick design tips when you're planning this out. Look for app notes for your chips. That's the term you want to look for, app note, application note. You can almost always find example circuits from the manufacturer. That's the way you want to go. Try to stay 2 layers on your board whenever you can. It'll be a lot cheaper and a lot faster to make. If you're doing RF, you're always going to have to do 4-layer. If you're doing RF and you can, if you can, look for an integrated module. So it's got the chip and an antenna and then digital out to you, and you don't have to worry about any of the radio frequency stuff. If you're look for open source projects using the same thing. For example, when I did the Zigbee project, I did the rocket badge from Chaos Communications was a very similar board, so I was able to use them for reference. And you can always find someone who knows more and beg them for help. It works really well. So if you go to, now it's time go to make your boards. You can make your own at home still, sort of, depending what you want to do. Single layer is easy, 2 layer is pretty hard. You're not going to make 4. You might not want the chemicals you need around you. And it's so incredibly cheap now to just get them made commercially. It takes about a week and a half now for most places in prototype quantity. It's fantastic. Generally, when you go to make a PCB, they want to make a giant panel, 14 inches by 16 inches or something. It's not really cost effective for them to make one off, so it's hard to find a company that'll make you just one. If they will, they still want you to make a full panel, so you can make a full panel at $120 or whatever and get 80 boards out of it, but if you screwed up, you're going to have a bad time. So there's a bunch of companies out there or groups that will batch together orders from a bunch of people, turn them into one giant panel, and then the company ships it back to them, they break it apart and mail it back to you. End result, $10 for a board. It's great. So some of those groups, OSH Park, it used to be Dorkbot PDX. It's currently, I believe, our favorite. Lane is great. He'll help you out with stuff. There's Batch PCB, which is run by SparkFun. There's a ton of other groups. If you're manufacturing something, pick who you're going to get to manufacture it first. Look at their specifications. Don't make traces too small or holes too small that they can't handle. So, quick tutorial on soldering. Who's tried to solder a project? How'd it go? Good? Yeah. Did you end up with a blob of solder that you kind of shoved around that didn't stick to? Yeah. Okay.
You need
Me
flux.
too. You need flux. Did you buy your iron at Radio Shack? So, it's sort of the opposite of photography. I think that soldering is about 5% skill, 5% knowing the tricks, and 90% having a couple decent pieces of gear. If you have a crap soldering iron from Radio Shack, you're probably going to have crap results. It's just, it goes too hot, it burns off the flux. It's not anything you did. It's extremely difficult to do anything useful with a piece of crap equipment. Fortunately, the good equipment is really pretty cheap. So fortunately, solder wants to stick to the metal. It doesn't really want to stick to the air. It doesn't want to make bridges if it can avoid it. It doesn't want to stick to the coating on the circuit board. It's explicitly designed so that solder won't stick except to the metal parts. The magic sauce is flux. It's what makes the solder runny. When you put the solder on your iron and all the smoke comes off it, it's the flux burning off, and now your solder isn't going to flow. You will ruin anything with a crappy iron. There's a bunch of demos. I'll have this link again at the end on the last slide for the Q&A part. It's a lot easier to just go watch a couple YouTube videos linked here than it is to try to explain them. But so some quick tools. Did you get getting a good iron? Did you get it from Radio Shack? Unless you're doing wood burning, it's probably crap. You really need something with a good temperature control. Hacko and Weller are great brands to start with. You can get a good Hacko for $80. Just get one. Your life will change if you've tried to solder something before. You basically only need 2 tips for most of what you're doing. There's a chisel tip. You don't really want the round tip because the solder will just spin around it, but with a chisel tip, it's flat, so it looks like a chisel. So the solder will stick to one side, and you can put it where you need it to go. If you're doing a lot of soldering like the QFP packages with tons of legs in a row, a bevel tip. Hacko makes a couple of great ones. You can seriously solder an 80-pin chip in under 30 seconds. Because you just go, done. And there's a video of it.
With flux.
With flux. Flux is the bacon of soldering. You can never have too much. When in doubt, add more flux. Whatever you're doing with soldering, if you're having a problem, add more flux. Get the no clean version, get the non-corrosive version. You will be very sorry if you don't, because you will probably not be able to clean it off well enough, and then it will eat your board. Personally, I like Chip Quick. You can get it on Amazon. If you're trying to remove components and do more surface mount, hot air. They're cheap. If you're never doing surface mount stuff, you probably don't need one, but you can get hot air for even less with an embossing tool at a craft store. I'm going to skip this because we're running low on time. You can build your own vacuum placement if you're doing reflow soldering, where you're putting all the parts on the board and then heating it all up at once. So you can just take, a pump from Walmart and a Bic pen and some aquarium tubing and any sort of pneumatic pedal, or probably even a couple pieces of 2x4 and some duct tape to pinch the hose. When in doubt, more flux. Some quick examples of stuff. So you can make stencils. So if you're going to solder a whole board at once, you put the paste through the stencil, kind of like toothpaste and silk screening. You should end up with it blobbed all over the board. And then you put all the components on it, and then you throw it on a hot plate or a griddle and cook it for a couple of minutes, and everything lines up. It's all good. There's a lot of videos. Question?
Yeah, you don't want to use that for food after that.
I wouldn't, unless you enjoy lead poisoning and wall candy.
We do, by the way, recommend actually using leaded solder, not lead-free solder for this kind of home hot plate assembly, because you have a much wider margin of error between the melting point of the solder and the point at which you destroy your components if you use leaded solder.
So if you don't use no clean flux, this is what happens. You can see where it kind of ate the pads off the board. Here's another example. Build a circuit board. It costs about $1.20 for that instead of a rat's nest of crappy soldered together, taped together wires. You could do that and spend a ton of time, or you could just make a circuit board.
Sometimes things don't go the way you expect, and you have to fix stuff that's broken. So you can sometimes just fly wire, we call that, which you just take a tiny little wire, like wire wrap wire, maybe 28 gauge, 38 gauge, and just solder it from point to point. Sometimes you can bridge from one place to another on the PCB with a resistor or something like that. This was an interesting one. You see that little hole near the, it's actually kind of a big giant hole near the USB connector. Dragorn was working on this project, and he found there seemed to be a short in one of the inner layers of a 4-layer circuit board, and he was just like, screw it, I'm just going to drill right through the whole thing, and hey, that removed the short. And for the rest of our 1 minute, we're gonna take it this time as an excuse to talk about a whole bunch of our projects that are related.
Fortunately, there's a bit of a break before you have to go downstairs, so we're going to run over. So Kisbee is a thing I did that talks 802.15.4, which is a protocol that lives under Zigbee. So SCADA control systems, power control systems, parking meters. I don't know why, but in San Francisco they all have them. Smart grid stuff. Pretty much anytime you hear smart grid or smart meter, it's going to be Zigbee. It's meant to be portable and battery powered. So Zigbee is low power, and it's low data rate. Twitter holds more data than a Zigbee packet. You can't see it with other tools because although it's in 2.4 gigahertz, it's a different encoding. There's other projects that do sniffing. Look up Travis Goodspeed's work, but he doesn't design for recreatability. If you're, I picked that instead of an SDR because I wanted low power, battery powered, hooked up to a mobile device and whatnot. There are other projects out there. There's the Fruituino, there's GoodFit hooked up to a radio, there's the AVR Raven that Josh Wright was using, but they're either not really meant to do sniffing, aren't easy to recreate, or, for example, the Raven needed the $400 programmer. So I was trying to be fully open software, fully open hardware. That's the existing version. The third version is going to be coming out hopefully soon, which is designed so it can be mass assembled. It uses its own dedicated Zigbee IC instead of doing SDR. It uses so little power that with a little, Minty Duino-sized charging pack, it'll run about 24 hours on a charge. It talks Bluetooth specifically to Android, so you can log packets where you are based on the GPS in the Android.
Dragorn sent me the very second probably prototype of the Kisbee. He got his first one working. He sent me one in the mail, and by the time it arrived, he had an Android app written for it. And I literally downloaded the Android app, turned the thing on, and it worked out of the box. First time he shipped a prototype to anybody, and it just worked. And I went war driving in 10 minutes after I got the thing in the mail. It was It's pretty awesome. Ubertooth, hopefully some of you guys have seen it. It's a little bit different because sniffing Bluetooth is hard for various reasons. One is that it's a frequency hopping system, and another is that packets are whitened or scrambled with the pseudo-random sequence. And we're out of time, but hopefully you guys can take a couple of minutes before we have like 10 minutes before the thing starts downstairs. So those of you guys who want to stick around, just FYI, we're running over a little bit. Also, Bluetooth packets have a funny feature in that they don't have a standardized synchronization word at the beginning of their packets like most communication protocols do. The synchronization word or the access code is specific to the particular device or target network that you're sniffing. And so these three things make Bluetooth sniffing hard, and I had to take an approach where instead of using a Bluetooth integrated circuit, I had to I originally thought I would take an SDR approach, try to make a software-defined radio that is special purpose, but I found this middle path. This middle path was finding an integrated circuit that could support the modulation type, which is 1 megabit per second frequency shift keying, and just have it stream all this 1 megabit per second continuously while it's tuned to a channel, and then do all my packet handling in firmware or in software on the host computer. So it's kind of an intermediate road between having the IC that does it all for you and the SDR type of approach where you do all this stuff in a host computer or a general purpose CPU or FPGA. Look like the Ubertooth. The shape and size of the circuit board is the same as the Ubertooth, but this is for sub-gigahertz radio communications, and if you've ever used the IMMe or seen that, the pink pager, it's a lot of fun to play with. This is basically the same radio chip in that, in a dongle form factor with some amplification. HackRF is a project that I'm working on. Betas are being manufactured right now, and this is a software-defined radio platform that operates from 30 megahertz actually to 6 gigahertz, and it's a dual conversion architecture that's low cost and low powered. The idea is I want to have something that I can put in my bag and carry around with me anywhere, and I don't have to plug it into a wall. I can just bus power it, and it'll operate on almost any frequency I'm interested in for any digital radio communications, and it operates both receive and transmit. It's open source hardware and software, and it'll be out soon. This is probably the most complicated board I've ever seen in KiCad, and it is, why don't you talk about this?
Yeah. So this board was designed by Jared Boone, who is ShareBrained if you look him up on Twitter or whatever. So this is the project that we are doing for Cyber Fast Track, where it is a platform for doing wired protocol capture. So it's a base board with an FPGA and USB 3 and a bunch of laptop memory, and connected to arbitrary front-end connectors that can do different things. So you capture at whatever layer you're capturing at. We're not quite at layer 1, but we're a little around layer 1 or 2. And then you can get everything above that and decode it. So for example, we're doing a gigabit Ethernet tap where it's a man in the middle, 2 Ethernet PHYs. You get nearly undetectable from either end, and it'll capture all the packets, process them in the FPGA, ship them up to you over USB 3, and then send them back out to the other device. So it'll be way cheaper than a commercial Ethernet tap.
I don't know that it'll necessarily be cheaper than some commercial Ethernet taps, but the man-in-the-middle approach should allow a lot of creative uses, and the modularity where we can plug in things like a USB 3.0 front end and do the exact same thing with USB 3.0. We have a front end where you can plug in and man-in-the-middle HDMI, et cetera, et cetera, et cetera. Yeah. Question? That's a really cool concept, and it's something that could be built out of our platform, we hope. Our project is focusing just on building the hardware and building software tools for monitoring, but there's a lot that can be done with injection and man-in-the-middle, and you could build firewalls out of these things. You could do a Tor appliance like you're talking about. There's lots of neat stuff that you could do with this as a development platform. So thank you guys for sticking around. I think we have yes. Yeah. In 5 minutes downstairs is, what is it? Wait, Don't Pull Me, which sounds like a lot of fun. So we're going to head down there, and we didn't really leave extra time. Oh, yeah, if you don't have one of my Throwing Star Land Tab business cards, if I haven't talked to you yet this week and you don't have one, just come up and grab one. And then we'll, ask us questions in the elevator on the way downstairs. Thanks, guys.